If we did live in a rotating universe, then time travel into the past would be possible.
Dr. Paul Sutter.
He's a theoretical cosmologist and a NASA advisor.
A research professor in astrophysics.
He's an award-winning science communicator and hosting several TV shows.
Not only is the universe getting bigger and bigger every day, it's getting bigger and bigger, faster and faster every single day. But we are not expanding into anything. And we are not expanding from anywhere.
Dr. Paul Sutter, thank you so much for taking the time. I actually wanted this conversation to really take a step back and look at a big macro scale of the universe.
I love it. I love it. That's my deal. I'm a cosmologist and we study the universe.
I think the best way to start is to start at the beginning, which technically might not be the beginning, but we'll get into that. And that is with the Big Bang. So what exactly is the Big Bang?
Right. The Big Bang, you're right. It's not the beginning. A lot of people think of the Big Bang as the beginning of the universe. But the truth is, we have no idea what the origins of the universe truly are. We do not know where the universe came from. We do not know why the universe exists rather than not exist. We do not know why there are physical laws when there didn't have to be physical laws. We do not understand the origins of the universe. And in fact, we do not understand its very earliest, trillionth of a second moments. But after that, we do understand it. We do have a surprisingly solid understanding of the earliest moments of the universe, and we encapsulate that in the Big Bang Theory. And the key statement, the key story of the Big Bang Theory, where everything goes, is we live in an expanding universe. The universe is getting bigger with every passing day. That means in the past, the universe was smaller and hotter and denser. That is the Big Bang. That's it. That's it. That is our story. You can summarize all of modern physical cosmology with that one statement alone.
And are there any specifics about the early universe and the Big Bang that we have found out recently? And how did we get to those conclusions?
Oh, fantastic question. So we arrived at these conclusions. The first time we cracked open the door to the Big Bang Theory was in the early 1900s. And we actually came about it through two separate paths. One, it was based on pure theory, and one was based on pure observations. And the pure theory side was the development of Einstein's general theory of relativity. This is our theory of gravity. And we believe at the very, very largest scales, gravity is the only force that matters. And so you can ask hey, if I've got a universe full of stuff about stars and galaxies and gas clouds and whatever, what does it do? Does it evolve with time? Does it change? And the equations of general relativity naturally predicted that our universe should be dynamic, that it should be evolving, that it should be either contracting or expanding depending on how much stuff is in the universe, and that a static eternal universe is actually a very fragile state. It's a very unnatural state, and that if you were to freeze the universe in place and you just breathed on one particle, it would set in motion a chain reaction that would set the universe back in motion again. Our universe wants to move. It wants to either expand or contract. That was on the theory side. And then simultaneously, we started making observations of distant galaxies and realized that every galaxy on average is moving away from us. And that the farther away you go, the more distant galaxy you observe, the faster it's receding away from us. This shows us that the universe is expanding. And that right there, those were the cornerstone theory and observations behind the Big Bang Theory. After that, after you make that conclusion that, hey, the universe used to be smaller in the past and it's going to be bigger in the future, once you make that statement, you are able to make a bunch of predictions, because you can predict what the universe used to be like in its past and see if there's anything you can observe, anything you can look at. And one of the biggest things you can observe is if you go back in time, billions and billions of years, The universe gets smaller and smaller and smaller. The further back in time you go, it gets denser and denser and denser. You're taking all this material and cramming it into a smaller volume. And you can go all the way back about 13.7 billion years ago, and you reach a state where the universe is about a millionth of its present size. And when it's a millionth of its present size, the density of matter is so high, the temperatures are tens of thousands of degrees across the universe, and our universe is a plasma, a state of matter, highly energetic state of matter, where electrons are ripped off of atomic nuclei. Everything's a hot mess. Then, as the universe expands from that stage, from the plasma stage, it cools off. And when it cools off, it releases a flood of radiation. And this radiation completely and totally soaks the universe. And in fact, this radiation is present even today. And it is in the form of microwave radiation. It completely blankets the sky. It completely soaks the entire universe. It is the leftover light from when our universe was very young and very small and very hot. That observation was made in the 1950s and really cemented the Big Bang Theory as the story of our universe. And from there, we've been able to make predictions about how much hydrogen and helium should be in the universe. We've been able to make predictions about how galaxies grow and evolve over billions of years. We've been able to make all sorts of predictions and measurements that align with this basic story that the universe used to be smaller in its past.
Didn't Einstein also have, I believe he called it his biggest blunder with his cosmological constant? What was the story behind that?
Yes, this is a great story of scientific development because prior to the early 20th century, prior to the development of general relativity and the discovery that galaxies are receding away from us, astronomers assumed that the universe was the universe, that it was static, that it was eternal. That, yeah, you can have planets orbiting stars, you can have stars buzzing around, you can have, spiral arms on galaxies, you can have supernova, the universe can have dynamic stuff inside of it, but the universe as a whole has simply always existed, it's always been here, and it doesn't change. And then Einstein developed general relativity, and he's like, hey, I wonder if this describes what this says about the universe. He found through his equations that, general relativity predicts a naturally evolving universe. The universe should not be static. It should not be eternal. It should be dynamic and evolving. But this went against the common conceptions, and also we had no observations yet that the universe was dynamic. And actually, this is very, very rare for Einstein, and why he called it his greatest blunder, because usually Einstein was very, very good at trusting the math, trusting his physical insight, trusting his gut, and that if he came up with a theory or an idea or a hypothesis that violated known observations, he would say, well, all the observations are wrong. Maybe you should go back and double check. And he'd be like right every single time because he's Einstein. And this is like the one time where he got a little nervous, where he retreated a little, where his equation said, hey, Albert, the universe should be expanding or contracting, but whatever it is not static. And he retreated from that, and he did have the freedom in his equations to add a term that essentially maintained the static nature of the universe. And he called this term the cosmological constant. And then just a few years later, Edwin Hubble would discover that the universe is expanding, galaxies are receding away from us, and he had to go back and scribble out that cosmological constant because it turned out it was wrong, and he called it his greatest blunder.
And wasn't there something later that, we ended up using the cosmological constant, he called it his greatest blunder, but it still ended up being useful in some way?
Exactly. So this is just how science goes, where Einstein added this extra term in the equations that the universe was naturally going to be contracting or expanding. So he added this term to fix it, to hold it in place, to add a source of pressure or tension on the universe to hold it in place. Turned out the universe was expanding. You can get rid of the cosmological constant. But then in the late 1990s, we discovered that not only is the universe expanding, but the expansion rate is going up. The universe is accelerating in its expansion. The universe is accelerating in its expansion. Not only is the universe getting bigger and bigger every day, it's getting bigger and bigger, faster and faster every single day. We have no idea what's causing it. We do not understand this. It still fits within the broader Big Bang story, because the Big Bang story is simply we live in an expanding universe. But now we're finding ourselves in an epoch where that expansion is accelerating. We call this effect dark energy, which is a super cool name, but we have no idea what it is. But when we go to mathematically model it, when we go to say, okay, we don't know what it is, we don't know what's causing it, but we know what's happening, and we can capture that action, that acceleration in our equations. Wouldn't you know it? It takes the form of a cosmological constant, an extra pressure, an extra tension in the universe that is doing something to the universe. Now, Einstein tuned that cosmological constant to stabilize the universe. That value is wrong, but the presence of the cosmological constant is still valid in our equations. We have no idea what causes the cosmological constant, but dang it, it's there. We can't ignore it.
I don't know why. I've always had this idea of the Big Bang being a single point in space expanding. Like, I always think in Infinity War, like Wong, he goes and he's like, in the beginning of the universe, Big Bang sent 6 Infinity Stones. And they show like a visual where it's like a single point that explodes. And then I realized, no, that's not it. It's just the universe. Why do you think the common idea of the Big Bang is it's a single point rather than just the universe?
Part of it is the name. And the name Big Bang was actually coined by an opponent of the theory. This idea of the Big Bang actually didn't have a name when it originated in the 1920s, 30s. It wasn't until the 1950s that an astronomer by the name of Fred Hoyle, who was dead set against this idea, who was giving a radio interview, and he referred to this theory derisively as the Big Bang. And you can hear it, you can play it. Later on, he would say, oh, no, I wasn't meaning to disparage it, but you can listen to the radio. You can hear the derision, dripping out of his voice when he says this. And the name stuck because it's very evocative. It's fun to say. It's very imaginative. But the idea of a Big Bang, we naturally, even me, if you just walked up to me on the street and said Big Bang, I would have in my head a visual of an explosion. But we're talking about the universe. The Big Bang can't be an explosion in space. It can't be a location in space because by definition, the universe is all the things. It's all the stuff. You can't have an explosion in space and call that the universe because space itself is the universe. There is no such thing as outside the universe because the universe is all the things. And so the Big Bang was not an explosion in space. The Big Bang was an explosion of space. And it's an explosion of space that is continuing to happen even today because the universe is getting bigger. The Big Bang happened right here in the room I'm sitting in. And the Big Bang happened in the room you're sitting in. It happened all throughout the Milky Way galaxy. It happened in the Andromeda galaxy. It happened throughout the entire universe simultaneously. The Big Bang was not a point in space. It was a point in time. It occurred in the past of every single object in the universe. We can all trace our roots through time and space back to this origin point that we all agree on happened in a finite time in the past, but that event occurred throughout the entire universe.
And so this event, we don't really know why it happened, but there are still theories. Where is the scientific community on this idea of like models in terms of how the universe came into existence, why we exist. Where's everybody leaning on that at the moment?
These are wonderful questions, and we're actually not leaning in any one particular direction or the other because we have a lot of really, really cool ideas, but these are highly speculative. And this is because the closer you get to the Big Bang, or the further back in time you go, we know that our universe, as we currently understand it, is 13.77 billion years old. And we can model it. We can use our knowledge of physics to go back in time. Like, we understand when it was a plasma state. Man, we know plasma physics. We can make those calculations. We can make those predictions for the cosmic microwave background. We can set the clock back all the way to when the universe was only a few minutes old. When it was a few minutes old, that's when it was fusing hydrogen and helium. And you know what? We have a pretty good grasp on nuclear physics because we have nuclear power. We have nuclear bombs. We've done all the work. We understand that physics. We can understand the state of the universe when it was only a few minutes old. But the further back in time you go, the harder the physics is, the more complicated the physics is, and the more mysterious the physics is. So we have some guesses and ideas of what the universe was like when it was, say, a second old or a fraction of a second old. But you get to a point in general relativity called the singularity. And this is, all of our calculations show that the universe goes all the way back to being an infinitely tiny point where you take everything, every single bit in the universe, whether it's finite, infinite, doesn't matter, you crowd it all down into an infinitely tiny point. We know this is incorrect. We know this is a wrong answer. This is a sign that general relativity, our understanding of gravity, is giving up, saying, hey, gravity is too strong here on too small a scales. I don't know what's going on. Here's infinity as the answer, an infinitely tiny point, because I just give up. I just quit. You know, it's Friday at 4 p.m. and I'm done, and I've been working all week. We know, or we hope, that a correct answer to what is going on in the extremely early universe will come to us from a theory of quantum gravity, a theory of gravity at extremely small scales. We do not have that theory. We do not have an accurate description of what the force of gravity does at extremely tiny scales. We just don't. We have speculative ideas. We have some very fun brainstorming sessions. We have some very cool ideas that navigate, like what could spark a Big Bang? What are maybe some other physical processes that could lead to something that looks like a singularity and would be the origination event for the Big Bang? But they're just ideas. We're just throwing stuff on the chalkboard, putting it out there, seeing if we can use any of these ideas to come at a quantum theory of gravity. But until we do, we got nothing.
Do we think this quantum theory of gravity, if it solves for the initial singularity, could also tell us what the singularity at the center of black holes is also like?
Yeah, that's the idea, because the Big Bang singularity is not the only singularity that appears in general relativity. Singularities also appear at the center of black holes, where if you take enough matter and compress it down into a small enough volume, then gravity overwhelms every other force and just keeps pulling and pulling and pulling and pulling. And you follow those equations out, you see what happens to the matter, and the matter gets compressed into an infinitely tiny point, a singularity sitting at the center of a black hole. Once again, we know that's wrong. We know that's a wrong answer. Singularities do not actually exist, but we don't know what actually exists. We don't know yet what the correct answer is. And again, we believe and we hope that the correct answer lies in a full theory of quantum gravity, a theory of gravity at very, very tiny scales. And if we can answer that, if we can answer the question of a black hole singularity, we probably have a good shot at answering the question of the Big Bang singularity and vice versa.
So why can't singularities exist? In my estimation, it's kind of like because infinities can't exist, but is that the real reason?
It's not so much that infinities can't exist, it's that the equations themselves are tools that we use to understand. We ask the question like, hey, black hole, if I drop a particle into you, I want to follow that particle's evolution. I want you, general relativity, to tell me what happens to this particle as it falls into a black hole. And general relativity says, okay, sure. So it falls through the event horizon, gets trapped forever, and it follows a spiraling free fall path, and then it goes to the singularity. And I say, okay, once it reaches a certain threshold at the singularity, what does it do? And the equations just blow up. They diverge. They do not give results anymore. They do not give sensible answers anymore. When I say, what does a particle do near the singularity of a black hole, the equations of general relativity stop answering my questions. They stop texting me back. They stop answering my calls. The infinities, the singularities that appear in general relativity are a dysfunction of the theory. They are telling us that the theory is not capable of describing what actually happens. The tools are inadequate. So it's not like infinities can't exist in nature. It's that infinities, when they appear in our equations, they render our tools useless.
So speaking of infinities, I kind of want to go into the nature of the universe a little bit and kind of get what the physics community or the evidence for and against is to the question of whether or not the universe is infinite.
Oh, very, very fun question. So we need to carefully define what we mean by universe, because there is a limit to what we can see. We call this the observable universe. And there's a limit because the universe is only so old. It's only 13.77 billion years old. And light has a finite speed. It only travels so fast. So whatever the true size of the universe is, we can only ever observe a small portion of it. There is a limit to what we see, a portion that has been illuminated so far, a portion where light from distant galaxies or the cosmic microwave background after 13.77 billion years has finally reached us. That's a finite bubble. That bubble is about 90 billion light years across. That is the limit of our observable universe. That is definitely finite. And that definitely has an edge, because there is a part of the universe that we can see, and then there's more universe past that we can't see. There are stars, galaxies, intelligent civilization, podcast interviews, all of it will remain forever invisible to us. We will never be able to see those distant portions of the universe. We'll never be able to measure it, communicate with it, see it. There are parts of the universe, the vast majority of the universe is permanently cut off from us. So the observable universe is totally finite and totally has an edge. How big the whole entire universe is, we don't know. We suspect, based on our models of what happened in the earliest moments of the Big Bang, that the universe is at least extremely large. And by extremely large, I mean, say 10 to the 50 or 10 to the 60 times wider than our observable bubble. That's big. It could be infinite. The universe could be infinitely big. We don't know. And it's likely that we will never know, because we are forever limited by our observable bubble. We can only ever measure what's here in our little pocket, our little illuminated pocket of the universe. We can never measure its true extent. We can never measure what's beyond our little pocket. It's forever locked off from us. So this is what we got.
And if the universe is infinite, that would require, for there to be any sort of density in the universe, wouldn't that require an infinite amount of matter within that universe for there to be any sort of density?
Yes. So if the universe is infinite in size and it has a finite amount of, a finite density, then that means there is an infinite amount of matter throughout the entire volume of the universe.
And then wouldn't that practically be like a multiverse? Because like if you have an infinite amount of space and an infinite amount of matter, then there's an infinite amount of combinations that matter could take, or at least in terms of the like probabilities of the formations the matter could take. Isn't that practically just a multiverse?
Yes, this is one way to achieve something like the multiverse, where if the universe truly is infinite, and again, we don't know, but if it truly is infinite, then there are regions out there in the universe where matter just takes on every possible combination. Like over here in our illuminated portion, we got a Milky Way right here. We got an Andromeda over there. We've got a galaxy over there. We've got a large scale structure like this. And then if you imagine going in a rocket ship and going through the edge of the observable universe, because you can't, but let's pretend you can, you would encounter other galaxies and other arrangements of matter. You would encounter other cosmic webs, different patterns. And if you traveled far enough, you would see, basically every possible combination of matter there is.
Just a quick reminder, I made this channel only to talk to YouTubers. So any YouTubers, put them down in the comments and I will go through, look at their channel and see about getting them onto a future episode of the podcast. And then you can hit that subscribe button right down below to make sure you don't miss that episode when it does come out. If the universe isn't infinite, for some reason I had in my brain this idea that like if the universe isn't infinite, there's like walls breaking off the universe, but like that doesn't really seem to make sense. What would the universe kind of look like if it was finite?
If it was finite, yeah, the temptation is to think of walls cutting off the universe, but this doesn't work because what do walls do? They separate one area from another. There is a left-hand side of the wall and a right-hand side of the wall. There's an inside to the wall and an outside to the wall. But the universe is all the things by definition. If you put up a wall, your wall is like, well, there's something else on the other side of the wall. Even if the something else is nothing, even if it's empty, that's still universe. That's still part of all there is. So the universe has no edges, even if it's finite. The observable bubble of our cosmos does, but the whole entire universe has no edges. And this is one of the hardest things for everyone to wrap their head around, even professional cosmologists, to visualize this, which is we live in an expanding universe. Our universe is getting bigger every day. This means that if you were to go out in the universe and say, pause the expansion, take a ruler, really big ruler, measure the distance between galaxies, and then hit play, wait a while, then make that measurement again, your second measurement is going to be bigger. The distances between galaxies grows on average. There's some things like galaxies can collide at local small scales, but on average, on the big scene, the universe is just getting bigger. The space between galaxies is growing. But we are not expanding into anything. And we are not expanding from anywhere. The universe has no edge. The universe has no center. There is no middle. There is no center. There is no wall. There is no boundary. There is no edge. The universe is all there is. The space between galaxies grows with time. That's it in an expanding universe. And I admit, I will be the first one to admit, this is very, very tough to visualize, impossible to visualize. But this is why we invented mathematics. Mathematics allows us to explore the universe in a way beyond the limits of our imagination. Mathematics is a tool that allows us to describe behaviors in the universe that we can't necessarily visualize. It allows us to make predictions. It allows us to understand that we are correct, that our story is right, even if we can't imagine it.
I believe there's some theories about like the shape of the universe. Are there different like possibilities for the shape, and how would we figure that out?
Yeah, so the universe at the very, very largest scales can have a variety of shapes. We call this the topology and the geometry of the universe. So if our universe is infinite, it's just infinite. It's just infinitely big. But if it's finite, there is the possibility. In fact, if it's finite at some scale, this has to be true. In order for there to be no boundaries and no edges, this means that if our universe was finite, and you got in your rocket ship and you could punch past the edge of the observable universe, which you can't, but let's pretend you can, and you keep traveling and traveling and traveling and traveling and traveling and traveling, eventually you would end up at your starting point. You would come back to where you started. You would, without turning your ship, without making any movements at all, just following a straight line for a very, very long time, eventually, if our universe is finite, you would come back around and come back to your starting point. You would come back to Earth. It might take you a while, like, a trillion years or whatever, but you would come back to that point. This is the overall shape of the universe. The universe at very, very large scales could be curved in one of these dimensions. It could be curved in all of these dimensions. It might be infinite in one dimension, but then curved in another, like the surface of a cylinder. It might be curved in all of its dimensions, like a three-dimensional sphere, which is very, very hard to visualize, but there it is. And absolutely, as far as we can tell, our universe has a particular geometry which we call flat, which means we detect no evidence for any curvature at large scales. However, we know that the universe is very, very large compared to what we can observe in our observable bubble. It's like trying to measure the curvature of the Earth being limited to just your backyard. The Earth is so gigantic that even though it has a curvature to it, it has a geometry to it. And if you travel in one direction long enough, you end up in your starting point. But if you're constrained to only make measurements in your backyard, you'll think the Earth is flat because you won't be able to detect that curvature. We've made very, very precise measurements of the curvature of the universe, going back all the way to the earliest moments of the Big Bang. As far as we can tell, the universe is flat to 1 part in a million. No signs of curvature to 1 part in a million, which means this is one of our indications that the true size of the universe is 10 to the 50, 10 to the 60 times larger than what we can observe in our local patch. Because if our universe was smaller, by now we would have picked up some hint of that overall curvature at large scales, but we see absolutely no hint of any curvature whatsoever, which gives us a clue that the universe is probably incredibly large.
Is it possible that the universe's shape could be something like pentagon or an octagon where like part of it is flat and it goes like in angles? So like any section of the universe, you would never be able to see any sort of curvature until like certain parts it's like straight down, or I don't know how to visualize that, but is that possible?
It is possible for the universe to be actually, this gets into the wonderful world of topology where, you can have completely flat universes. And by flat here, we have a geometric test, or we have many geometric tests for curvature. One of those is by measuring how parallel lines behave. On a flat piece of paper, parallel lines will stay parallel forever. This is Euclidean geometry. But if I put parallel lines, say, at the equator of the Earth, and I follow those parallel lines up, and each line just always goes north, 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 north. Eventually they intersect. Eventually they cross. Those parallel lines do not stay parallel forever. That is an indication that the curvature of the Earth is more than zero, that the Earth is curved. It is possible to have a sense of curvature with a completely flat universe. And an example of this is a cylinder. So if I take a flat piece of paper and I draw 2 parallel lines on it. So the flat piece of paper is indeed flat, mathematically, geometrically flat. But then I take the long side of the paper, and I wrap it around to form a cylinder. And I look at my lines that I drew. You can do this at home. Now, at-home cosmology experiment. You wrap your cylinder, you make your cylinder. You'll see that your parallel lines are still parallel. That universe is still flat. It has a different topology.
But in a cylinder, we still have those like cutoff edges there. Like if there are no edges, unless it kind of like pinched off at the end, would it still be able to have those like flat edges of the edge of the universe?
Yeah. So the flat edges, that's I like the way you're thinking. The flat edges are a consequence of pretending that we can visualize the universe, because the universe has no edge. That has no border. If our universe were a cylinder, what that means is that in one direction, say this direction, it's infinite. I can go off in infinite direction. But in this direction, if I travel and go forwards, I will end up back where I started. But any dimension that is not closed, that it does not loop back on itself, is infinite.
So a like kind of more sharp edge of the universe that isn't really curved, that's not really possible?
It's not really possible, because what you're doing when you're imagining the sharp edges of a cylinder, that cylinder is a two-dimensional object. You only need two dimensions, two variables to describe the surface, any point on the surface of that cylinder. And then you are embedding that, you are imagining it in a three-dimensional world. So you're cheating a little. You're coming up out of the perspective of the cylinder. You're coming up into a third dimension and looking at the edges of the cylinder. But if you were to live on that cylinder, that's it. You live on the cylinder. That is your entire world. It is possible for our three spatial dimensions of the universe to exist in a larger four-dimensional construct, where there is a large fourth dimension of space. We call this the bulk. There are some very hypothetical ideas out there based on string theory, where our universe, our three dimensions, are just what are called a brane, which is short for membrane, that exists in a larger structure called the bulk. This has some very intriguing connections to explaining why gravity is so weak, what could have triggered something like the Big Bang. These are very cool ideas, but once again, very speculative ideas. Our three-dimensional universe, finite, even if it's finite, does not need a bulk. It does not need to exist in a higher dimensional space. You have everything you need to completely, adequately describe the universe, a three-dimensional universe with the mathematics at hand, without needing extra dimensions.
And if it's a finite universe, is there any chance that it's spinning the way that Earth spins?
We've actually done a lot of measurements on this to see if the universe is spinning, and there's no indication whatsoever so far that the universe is spinning. There's this interesting anecdote. So Albert Einstein was very good friends with a mathematician named Kurt Gödel, and aficionados of mathematics will recognize Gödel's name for the Gödel incompleteness theorem, which plays a major prominent role in mathematics, but he also dabbled in general relativity, and he discovered that if the universe was rotating, if we did live in a rotating universe, then time travel into the past would be possible, because you could follow a very particular path in this rotating universe. You never exceed the speed of light. You can take your leisurely time, and you're always putting one foot in front of the other, but then you arrive into your own past. That was, I believe, the first example showing how time travel is possible in the general theory of relativity. It's only possible if the universe is rotating, but there's no observations whatsoever that suggest that it is.
And how would we test that the universe was spinning? Like, what kind of test did we do?
One of the biggest tests we can do is to look at the light of the cosmic microwave background, this light that was emitted in the very early universe. And that light has traveled through the universe for billions of years before it reached the Earth. And we can look at it in all directions on the sky. And if the universe was spinning, then as that light from the cosmic microwave background filtered its way through us, the universe would be spinning. The universe would be misaligned with what we see in the cosmic microwave background. But when we look through objects, say large clusters of galaxies, through those clusters onwards to the cosmic microwave background, everything lines up. And if it did not line up, that would be a sign that maybe our universe is rotating at very large scales. But everywhere we look, everything's all nice and lined up.
And so we started out with the beginning of the universe. We kind of went into a general idea of like the shape, nature of the universe. Now I kind of want to go on to the end of the universe. One of the actual theories about kind of more the start of the universe is the fact that the universe expands and then contracts, and then that's where the singularity came from in the first place. That would mean there isn't really much of an end of the universe. It would just kind of come back down. Is there any evidence that the universe might be contracting back down to a big crunch?
Yeah, so right now, as far as we can tell, it's the exact opposite, where not only are we not contracting, but our expansion is accelerating because of this mysterious thing of dark energy, which we do not understand what causes dark energy, but we can see its effects played out. And for the past roughly 5 billion years, our universe has been accelerating in its expansion. It shows no sign of slowing down. It shows no sign of stopping. It shows no sign of reversing and leading to a big crunch. That said, we do not understand dark energy. We do not know what tricks it might have up its sleeve. We do not know what it might do billions or trillions of years from now. It might transform itself. It might decide to do something else. Until we get a good handle on the nature of dark energy, it's very, very difficult to make long-term predictions for the universe. That said, it's like a weekend weather forecast. If the present trends hold, if dark energy is just a cosmological constant and it's here to stay and it's not going to change, then we can say what the fate of the universe is, but that is subject to our present understanding.
And so what would the universe, assuming we don't have a big crunch, what would the ending of the universe really look like?
It's going to look really sad and depressing and dark. And that is because the dark energy expansion is going to rip everything away from us, where it will accelerate the universe and continue to accelerate the expansion of the universe. Galaxies will get pulled away from us faster than the speed of light, which means they disappear from view entirely. They get dimmer and dimmer and more redshifted, and then they just vanish. We will be left alone with our nearest neighbors, the Milky Way galaxy, Andromeda, Triangulum, and a few other small dwarf galaxies. We are all gravitationally bound together. We are all holding on to each other. We will resist being ripped apart by dark energy. We will all collapse together. Actually, starting in the next 5 billion years, our galaxy will start merging with Andromeda. All of our nearby neighbor galaxies will merge into one big mega galaxy. But there's only so much matter. There's only so much material, gas in a galaxy, even a big merged one, which means there's only a finite amount of material for making stars. In roughly 10 to 100 trillion years from now, the very last stars will be born. They will deplete the remaining gas reserves. And about 10 trillion years after that, those stars will die. And we'll enter something called the degenerate era. This is the era of the leftovers, where no more stars will be shining from nuclear power. It will just be the leftovers. It will be the remnants of stars, white dwarfs, neutron stars, black holes. Planets will be still hanging around, asteroids, bits of debris. Eventually, all of those stars will decay. So the white dwarfs will turn into black dwarfs. The neutron stars will slow down and probably convert to black holes. Eventually, the black holes themselves will dissolve through a process called Hawking radiation, where they slowly emit radiation. Over the course of 10 to 100 years or so, all those black holes will go away. At even longer time scales, various quantum processes will eventually dissolve all macroscopic objects. So any large-scale object will simply diffuse over the course of 10 to 100, 10 to 200 years. All you'll be left with will be a foam of the lightest subatomic particles like electrons and neutrinos and radiation. Anything outside of our local bit of what remains of the Milky Way galaxy, this like foam of subatomic particles, the accelerated expansion of the universe will be so strong that if one of those particles just strays a little bit too far out, it will be picked up by the accelerated expansion and ripped away. And eventually, after enough interactions, all of it gets ripped away, all of it dissolves, and the universe as we know it will be completely unrecognizable because it will just be individual particles like electrons and photons separated by accelerated expansion of absolutely nothing. The average temperature of the universe will plummet to near absolute zero. It won't reach absolute zero, but it will slowly coast down to absolute zero. And as the temperature of the universe continues to drop, this makes temperature differences impossible to achieve. And so you will not have without any temperature differences, there will be no flow of heat, which means there can be no thermodynamic work, which means eventually the universe just grinds to a halt. And we call this the heat death of the universe. It is the death of heat. It is the death of available energy. And the ultimate extreme far future of the universe painted in this scenario is just a sea of subatomic particles spread light years apart, slowly cooling to a temperature of absolute zero.
And I heard one thing. There was some podcast I was watching a while ago with Roger Penrose, and he said something like the heat death of the universe looks pretty similar to what maybe we think the singularity at the beginning of the universe looked like, just at a different scale. Is that really the case, that it's just different size, but it looks pretty similar?
Yeah, this is Penrose's idea called Conformal Cyclic Cosmology. And it's in this idea where if you race out this universe out to its most extreme time scale, then what happens, and if all particles eventually decay to something like photons, and you're left with just one photon in one patch of the universe, then this maps onto the Big Bang through some mathematical trickery, where you can like rescale the conditions of the Big Bang to make it look like any one of these patches. Honestly, most people don't take conformal cyclic cosmology very seriously because it makes a lot of very bold assumptions about the nature of the universe and, frankly, the nature of fundamental physics. It's not clear at all that all particles decay into just photons. Like an electron just stays being an electron, a neutrino just stays being a neutrino. It's a very cool idea. It's a very interesting idea. It doesn't seem to be correct because it doesn't match up or line up with what we do understand about the Big Bang and about particle physics. But hey, crazy ideas are more than welcome because we don't really know what's going on.
Yeah, that still is one of my favorite theories of the universe, is like the idea that it's so big that we have no idea how big it is because of like photons, and then it just explodes again. Just, man, it's such a cool idea.
It's a fun thing to think about.
And so I wanted to go a little bit onto God's existence, but I know you don't talk about your personal beliefs publicly on this matter, but I was wondering if there's any sort of evidence or ideas that you've come across in your work or through studying that you think should be either included in this conversation or maybe an answer to a question that is usually put forward in these sort of discussions about God's existence.
No, honestly, the Big Bang Theory sits aside and beside and different from the question of the divine, the question of God or God's existence. There are many cosmologists who are atheists. There are many cosmologists who are agnostic, and there are many cosmologists who are theists, who are very faithful and devout to their faith. And no one sees any conflict. No cosmologist sees any conflict between what they are doing and their faith, because if you don't believe in God, then you're just investigating the nature of the universe, just like other physicists study high energy particle systems or condensed matter systems or thermodynamic systems. We're just studying cosmological systems. It's like something fun to think about. And then if you are very devout, then nothing you're doing, nothing you're researching or studying or revealing changes your faith. If you believe in God or gods and that they work in divine and mysterious ways, okay, then you're just opening the door to that and you're gaining some understanding to that, which can be a very rewarding and beautiful thing. And so these are separate trains of thought. These are separate modes of inquiry. We do live in a very beautiful and mysterious and largely unknown universe. There are many ways to attempt understanding of this universe and inquire into the nature of the wonder that we exist in. Whether it's through faith and theology, whether it's through philosophy, whether it's through physics, whether it's through art and music and dance, we all find ourselves, on this planet existing in a universe that no one really asked for and no one really understands. And we're all just trying to figure it out in our own way.
And looking back to quantum gravity, I found that really interesting because I've never really understood why these two models of quantum physics and general relativity don't work together. Is it just in the equations or is it something different?
Yeah, there are very deep both in the sense of equations and in the sense of fundamental worldview, but the differences between these two branches of modern physics. In terms of the equations, in quantum mechanics, we use quantum mechanics to describe every force but gravity. We use it to describe electromagnetism, weak nuclear, and strong nuclear. And we've developed a very powerful mathematical tool set. It's a little bit unwieldy and it's a little complex, but it is powerful to describe those three forces. And that tool set is called quantum field theory. But when we try to apply that tool set to gravity, we say, hey, what does gravity do? If we treated it like a quantum force, just like all the other forces, what does it do? All of our techniques fail. Everything just gets screwy and divergent and makes no sense. So the tools that we have developed to describe three forces of nature do not apply to the fourth because everything just goes haywire. And one of the reasons it goes haywire is this fundamentally different worldview, which is in the general relativity picture of space-time. Its fundamental assumption about space-time is that space-time is smooth, is that there are no jagged edges, there are no gaps, there are no holes, that at the very, very smallest scales, general relativity, for the math to work in general relativity, it must assume that space-time is smooth, that the fabric of reality is smooth. But in quantum field theory, the fabric of reality is anything but smooth. You have these quantum fields vibrating in and out of existence. You have particles popping in and out of existence. You have something we call the quantum foam, which is at the very tiniest scales. Reality is this like chaotic, frothing mess. And this is going to disrupt space-time, and at the very smallest scales, space-time is a nightmare. They're bits and pieces of space-time. They're jagged edges, gaps opened up, tiny tunnels and wormholes propagate all over, and then they just fizzle away, and then they come back, and then they fizzle away, and it's just this nightmare. Quantum mechanics says that is the basic fundamental picture of spacetime, while general relativity says, no, the fundamental picture of spacetime is smooth. And when we try to merge those together, of course, our equations go haywire because there are different perspectives about what is happening at the very smallest scales in nature.
And if we were to solve this quantum gravity, is there any chance that it would solve some other problems that we have in physics, like dark energy, dark matter? Is there any way those are linked to our wrong view of quantum gravity per se?
Oh, this is a very, very real possibility. We can't guarantee. I think if aliens were to deliver us a theory of quantum gravity, we can't guarantee that we would be able to explain, say, the earliest moments of the universe or the nature of dark energy or anything else. But there's a strong suspicion that this is true. And that's why, one of the many reasons why we are so interested in things like the earliest moments of the universe and like dark energy, because, if we can learn something about dark energy, it might crack the door open to quantum gravity and vice versa. This might be places where quantum gravity, the quantum nature of gravity, is being made manifest in our universe. And so if we go study those manifestations, maybe we can figure out what's going on.
Before we end out, are there any sort of other astrophysics or cosmology things that have been on your mind recently?
Something that's always on my mind, something I study a lot, is something called cosmic voids. This is at the very, very largest scales. When we zoom out, most of the universe is empty. It's just completely deserted, empty patches stretching hundreds of millions of light years on the side. I am very interested and curious about cosmic voids. I've developed techniques for finding them in surveys, for understanding them. And I believe that they are windows into dark energy. Once you get rid of all the other matter, all the other stuff, all you're left with is dark energy. So if we want to understand dark energy, we have to go to where the matter isn't, and we have to plunge ourselves into the cosmic voids and hopefully find some answers there.
And in terms of dark matter, is that between galaxies, or is that within everything? Do we have an idea of if it is a particle, whether or not it's between things or kind of more diffused everywhere?
Yes, if the dark matter is a particle, then the true structure of the universe, if you were to snap your fingers and illuminate all the dark matter, you would see something called the cosmic web. You would see these long, thin tendrils, these dense clumps, and the galaxies themselves sit as little pockets of light pooled up in this much larger structure of matter. And so we do strongly suspect that the structure of the universe is much richer than we can observe, because luminous matter only illuminates a small portion of it.
And final thing, do you have any sort of final thoughts or any sort of messages that you would like to talk about as we end up?
Just always stay curious. Thank you for a wonderful interview. It was a delight to dig into these topics and answer your questions. And if people are curious, there's my podcast, Ask a Spaceman, also my YouTube channel, Near Futures. You can find those. You can find my website, pmsutter.com, and I have a few books out, How to Die in Space, Your Place in the Universe, and Rescuing Science. Those are all available nationwide. And really, I am here to help satisfy your curiosity.
Well, thank you very much. Of course, all of Dr. Sutter's books are going to be linked down below. And then you can also check out his channel right here. And then over here is going to be a conversation I had with one of Dr. Sutter's really good friends. And it's a really, really fun one, talking about aliens and astrophysics and other stuff just like that. So you can click that one. And thank you so much for watching.